Okay, so welcome back. And so now we're going to talk about another aspect of this idea, this tangent line problem, and I'm going to call it the velocity problem. So there's another way we could approach this idea of instantaneous velocity as it relates to a tangent line. Okay, so they're related to each other. So another way of looking at this is if we look at a particle that's moving. So we can look at a velocity as a rate of change in position over change in time. So we can approach it very similarly as we did in the last video with the tangent line problem. So in this case, we're going to want to know, hey, what is the instantaneous velocity of a particle moving along an axis over time? So the question is we're going to use average velocity. Well, not question, but what we're going to do is we're going to use average velocity to help us approximate or get an idea of what's going on with instantaneous velocity. So with average velocity, right? So if we look at average velocity, again, it's a change in position, right? So again, we're going to use s of t as a position function, right? So, and let's say we're looking at t equal to a. And so we want to know what the instantaneous velocity is. So we're going to use average velocity, average velocity. And we're going to go f of t, right, minus f of a over t minus a. And so this is going to be our formula for average velocity. Okay? And notice, again, it's analogous to the same situation that we dealt with the tangent line. Okay? So the definition of average velocity is given by this formula on the board. Okay, and the interval, so average velocity of time over time interval a to t, right? So this is for t in the interval from a to t. Okay, and the other thing too is if a is less than t, right? So a is less than t. Okay, and I'll be giving these definitions later on. Okay, now here's the other thing too, is just like in the example that we saw with the tangent line, the closer a is to t, right, the closer this average velocity becomes or tends towards the instantaneous velocity. Okay, so that's the definition that we're going to use for instantaneous velocity when t equals a. Okay, because that's the instantaneous velocity, right? This is what we're interested in. We're interested in what the velocity is of this particle is when t is equal to a. But what we're going to do is we're going to choose another time not equal to a, right, on this interval, such that a is less than t, so that we get an average velocity. But keep in mind, the idea is that, hey, as a and t become closer and closer, right? Okay, so as this time that we choose gets closer and closer to a, the average velocity is going to become closer and closer to the instantaneous velocity. That's the idea. Okay? Okay, that's where we're going to stop. Oh, actually, no. Let's do an example. So here we have a rock. Okay? So in this example, we have a rock, and it's dropped from a height of 64 feet. Okay? So the height is 64 feet. Okay? It is determined that its height in feet above ground t seconds later for t from 0 to 2. So okay, so t is from 0 to 2. Not 1 to 2. From 0 to 2 is given by this position function. So here's the position function. It's negative 16 t squared plus 64. Okay? Now, they want to find the average velocity of the rock over each of the given time intervals. Use this information to guess the instantaneous velocity of the rock at time t equal to 0.5 seconds. Okay, so here's one interval. So A is 0.49 to 0.5. And the other time interval is 0.5 to 0.51. Okay, so what are we doing here? All we're doing is we're going 1/10 of a second before 0.5. So we're going 1/10 of a second. No, actually 100th of a second, right? Before 0.5. And we're going 100th of a second after 0.5. And so what we're going to do is we're going to use both of these, the average velocity based on both of these intervals to come up with an idea of where the instantaneous velocity might be. So let's do that. So again, we're going to use the formula. Average velocity, again, change in position over time. So it's going to be the average velocity equals what? It's going to be s of 0.5 minus s of 0.49 divided by 0.5 minus 0.49. Okay? Now, if I plug this into my calculator, right? So this is where you could use your calculator on examples and homework, okay? You'll be able to use a calculator for things like this on the exam or quiz, but again, you can do this with a regular calculator. You don't need a graphing calculator, okay? Okay, so now, if we plug this into the calculator, you're going to plug in 0.5 here first and get a value for s of 0.5. Then you're going to do the same thing with 0.49, and you're going to then subtract these two, which is going to give you 0.01, right? So that's easy. So now, if we plug it into our calculator, what you should get is negative 15.84. Negative 15.84, okay? Double check that. Make sure you get the correct answer, okay? So this is the average velocity in what? Feet per second, right? Feet per second. Where's the negative sign coming in from? Well, great question. What does the negative sign tell us? The negative sign tells us the direction that the rock is going. In this case, negative means it's going down towards the earth. Okay, so it's going in a negative direction down. Okay? Now, what about this part B? Well, we're going to do the same thing. Use the same formula. Okay? V average velocity, is again given by S. Now this time it's going to be 0.51 minus S of 0.5 over 0.51 minus 0.5. And these are approximate values. Okay, so now if you plug this in your calculator, what do you get? Again, double check. You get negative 16.16. Negative 16.16 feet per second. Okay. Again, a negative sign in this case, again, context is important. So in this case, we're talking about dropping a rock. So it's going down. So negative is telling us the direction. The number itself is the magnitude in absolute value. Okay? So the speed is the magnitude. So the speed is how fast the rock is moving without direction. Velocity includes the direction, but that's a little bit of physics. I mean, I know this is the calculus class, but again, this calculus is used in physics. Okay? Okay, so now, based on this, what would we guess is the instantaneous velocity at 0.5 seconds after the rock is dropped? I would guess 16 feet per second, negative 16 feet per second. So, or 16 feet per second downward. And that's it. So again, do some more examples, practice, and let me know if you have any questions. Have a great day.